So for lecture 10, we're going to continue talking about feature engineering and get into gradient descent, and we'll finish off gradient descent in lecture 11. But let's go ahead and think back to what we were talking about at the end of last lecture. So we had this idea of this relationship between miles per gallon and horsepower in this example we were going through. And we said before that if you take a linear approach to trying to model this data, you probably come away with something roughly like this, which not too bad. But the idea is that we could probably do better, and there's probably something that perhaps might look a little more quadratic like this, which could be a better way to model this data. And so we want to think about how could we build a hypothesis function that would allow us to work with this. How can we do this? And so this kind of leads us to the idea that we really want to think about the linearity in our parameters, and we very well can model things, with relationships like this, or like this, or like this, or even like this, But we have to remember that we need to be linear in the buildup of our model, and so we need to have something that satisfies the hypothesis vector. So that would be things like so in this case we have the our design matrix multiplied by our parameter vector, or dot product of our parameter vector, and that gives us our hypothesis vector. And in order to do that, we have to be able to take every single row of our design matrix and multiply it by all the values of our W vector, or our weight vector. And the only way we can do that is if we have some sort of if we have our problem set up such that we have linear combinations of our features. And so in order to do that, we have to have something that looks like this. Right, so we don't really care about what's too much going on in these question mark areas. What we care about is that the weights we have are being multiplied to this something, and then we're adding them together. And if you look at all of these here, it follows that principle. So we have W, 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 and W3. So this is W2. So here, W. So these are all good. What we can say is these weights are being multiplied by our features. So if we look at our features, these would be like the question marks. We have this, and this, this. So these features are these arbitrary polynomials, but when it's set up in this way, we have linear combinations of our features with our weight vectors, or with our weights, and that's just fine. We can't do that when we have things like this, because here we have information about our weights, and they aren't no longer linear combinations. They're doing weird things like being an exponent, or having weights that are inside some other function, and this is not good. This is going to break down, really it's going to break down this thing right here. So just to make that explicit. So we can't write this in terms of our really our augmented x vector dot product with our weight vector or parameter vector. So these are things that are stopping us from doing that. So this will mean when we say we have to be linear in the parameters. When we say that, you can kind of think about, and it's this. All right. So here's an example called Amdahl's law, and this isn't necessarily. I mean, it's just an example, so don't worry about memorizing Amdahl's law or anything like that. But this is just an example that we're going to use. And just to round out what Amdahl's law is about, it relates to the runtime of a program. So when we talk about how quickly a program is executed on a computer, we look at the number of processes and the parts of the code that can run on multiple processors at once. So we move by sequential versus non-sequential. We're talking about stuff that can be parallelized and cannot be parallelized. So for example, in this part here, this is stuff that is sequential. So sequential means it has to happen in sequence. So like 1, 2, 3, and it can't be parallelized. And then this part is the non-sequential part. And that's just stuff that can be parallelized. So that'd be where we have maybe something that comes here, and then it can now be done in parallel, and then comes back together. So the parts here are parallelized. Okay, so we have this data that we've collected right here, where the number of processes are being used, the time in hours tends to go down, and that makes sense. And so we want to kind of see if we can fit a hypothesis function to describe this data here. So let's go ahead and try doing that. We know we have a few things that we need to care about. We know that we need to, I'll put it down. So we care about our design matrix. We care about our parameter vector. And we also care about our predictions that we know about our y. So perhaps the processors and time, how many processors we have. We might predict how much time something's going to take. So in this case, processors would be our x, and time and hours would be our y. So we really only need to find out what the w is, because we can build our design matrix and we know what the y's are. So we just need to find w's that when we dot product them with our x, gets us as close to the y as possible. And whatever those w's are going to be our w star. They'll be our optimal parameter vector. And we use the normal equations to get what that is. The normal equations gives us that x dot product w parameter or parameter vector, and that gets us as close to the y vector as possible. So let's go ahead and write some of these things out just to be clear, and maybe I'll actually change some of these just to make it a little bit clearer. So we have our y, and we have our w. So let's go ahead and start with our design matrix. So we know our design matrix. We're going to have something that is a 3x2, and we know that we need to fit, maybe I'll write this in black, the form of our hypothesis vector equals the design matrix, product with our parameter vector. And so in order to have these two things be able to be dot product, we need to make sure that we can actually do this operation. So we know that our parameter vector needs to be a 2 by 1 because these two need to match. So let's go ahead and actually we'll just do our parameter vector first because that's super easy. We know that we have our W naught and then we have 1x, so we have our W sub 1. And we know in our design matrix that we're going to have our 3 ones. And we know that we have 1x, so we're going to add that in over here. And remember, we just can't put in these x's here. Like it won't be 1, 2, and 4. Now, it might have been that if this was just x, but it's not. We have to look at what's happening to the feature, and the feature is 1 over x. And we get that if we look back at Amdahl's law. So this is what we're trying to do. So W naught was easy. For this, we have to take this 1 over x. So that winds up being 1 over 1, and then it will be 1 over 2, and then 1 over 4. And really quickly, just to make it clear, I'll do that. Okay, so that gives us our design matrix, and we have our parameter vector, and we already know what our y vector is. That's just going to be 8, 4, 3 because we already have y. And this is a 3 by 1. Okay, so the whole point here is to find out what is the W naught and W sub 1. And that's going to allow us to determine what this hypothesis function is. So let's write that down because that's super important. So our goal and particularly not just the W naught and W sub 1 because there's infinite number of values that we could put in for there, but it's to find the best one, the W naught and W sub 1 star. The best one that gets us closer to the y vector when we solve the system of equations. And we do that by solving for the normal equations. And that's going to be the x transpose x parameter vector star equals x transpose y vector. And this is a system of equations, specifically a system of 2 equations. I'll put that in black. Because we have 2 unknowns. And the way we find out what W star is we know that by transforming this, we would get our optimal parameter vector is going to equal x transpose x inverse x transpose y. And this is going to, if we solve the system equations, we'll get what that W vector is, which is going to, when plugged into this, and solving for this, we're going to find out what W naught and W1, given this design matrix, is going to get us closest to this. And we know that there is a solution to this, and then one unique solution because x transpose x is invertible, because x is, in this case, full rank, and all of x's columns are linearly independent. So how do you know they're linearly independent? We can take 1 divided by the determinant of x, and the inverse will give us a square matrix. So that's one way that we can tell. If not, there'll be infinite number of solutions for this. So maybe let's write that down as a little bit extra. So here, x transpose x. So full rank. Or linearly, independent. And hopefully, if you hear my dog snoring in the background, it's not because he's tired, but it's also not because he's bored, because this stuff is not boring. As I say that with the most boring voice possible. Okay. So, we have this approach to kind of finding or fitting this hypothesis function. And, it's a pretty, it's kind of the approach that we've been taking all along. So this is, not saying that's should be entirely new to all of you, but it just kind of gives you a way of taking, an example of taking a data set and then kind of going through the motions of figuring out what these unknowns are and what we need to do in order to solve for these parameters. Because ultimately, when we do machine learning, we're trying to find out what these parameters are. Because if we were to get additional data and we have, let's say, we want to think about how much time it will take if we have 8 processors, well, now we can just plug that in to our hypothesis function. And if we have these weights, then we'll be able to find out what our prediction is, what the new y would be given whatever n processors we have. So this is how we go about solving this. And we can add on any other features that we want. If we had like more features like feature 2 and feature 3, blah, 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 as long as it doesn't get in the way of being linear in the parameters, right? So we have to kind of maintain this approach. So that's kind of the thought process that we're taking. Now, suppose we want to fit a hypothesis function like this, where it isn't linear in the parameters. So remember this from a few slides ago, right? It kind of looks like something like this, not linear in the parameters. And this doesn't follow our typical thing. This kind of, this feature here kind of looks something like this maybe. Purple. Be maybe something like that. So if we want to fit this and we want to kind of follow with what we've been doing, we need to do something to this feature here. This needs to change. We have to apply a transformation. So that's what we're going to talk about next, is how do we take something like that and how do we rework it? So, our goal is to get it into the form of, and I'll give you a second to guess, W naught plus W sub 1 times something that goes here, plus whatever Wn something. This is what we want, is this right here. So how do we take so we have to have some sort of transformation that does this. we need to get it linear in the parameters. So how do we do that? Let's go ahead and take a step-by-step approach. All right, so we have, let's see. Let's try to see if we can apply a transformation here to get this into a form that follows along with, yeah, more along this line, where we have linear combinations. So how do we do that? Well, maybe we'll do this in green. All right, so let's take h of x equals w naught times e w sub 1 x. Now, we know that at some point we need to break apart this wo and this e, and then at some point we want to deal with this e and w sub 1x. So how are we going to do that? Well, we know that we can get help from logarithms because we have an e, and when we're doing things like these transformations, we can use whatever we want. In this case, since we have an e, it makes sense to use the natural log, or log in base e, instead of something like log base 10. So we'll just assume that we're dealing with log base e here. We also know we have some nice properties of logarithms. So well, we know that log of a times b, or the product of log ab, is equivalent to log a plus log b. So we can use that to our advantage here. And that makes us very happy. Okay, so let's make this a little bit easier on ourselves. Let's just write this as we'll just write this as y. So here, just simplify this a little bit. So and we'll do log of y equals log of this entire thing. And we know from our property of logs that we can break this apart now. So it's going to equal log of y, which equals log of w naught plus log of e w sub 1 x. Okay. Now we also know, since we're using the natural log here, what we're assuming, that when we have log and e with something, we can essentially get rid of it. This will go away and just give us this up here. We have this log function, and we really want to be able to think about, what is it that we can, like, what exponent can I add, can I add on to e so that the output of e, or so the output is just e to the w sub 1x. And that idea there will allow us to cancel these out. But that's the exponent that you put on the base. So in this case, this will reduce down to log y, which will equal log of W naught plus W sub 1 x. Now, this looks like it's very, very close to the original idea that we had, which was W naught plus W sub 1 with something, right? So this was very close. Now, we want to be able to clean this up a little bit. It's sort of like U substitution, I suppose, where we're dressing this up with facade to make it easier to plug into the normal equations. And that means that we're going to have to eventually remove that facade later on and convert it. So one thing that we can do, we'll do this in blue. We don't have to do this, but we can say that this is going to equal z, and this will equal beta sub 0, and this will equal beta sub 1x. The betas are nice because in traditional linear regression, things are defined in terms of beta coefficients for your weights. So we're going to go ahead and have this be our final answer for how we're reducing this, plus the roadmap that we're going to have to provide. But this right here looks exactly like this. And the roadmap that we can apply to that is z will equal log of y, and beta sub 0 or beta naught will equal log of W naught, and then our beta sub 1 will just equal our weight. That's like a 1-for-1 because it's already in the form that we want. And for the beta sub 0, this will further have to be put into W naught star, which equals e to the beta sub 0 star. For this, that's fine because it's already in. These two are equivalent. But for this, it's what are we going to have to add into the exponent for the log base e to get our W star, the normal equations, and this will be what we plug into it. I suppose I can write that a little bit better. Okay, and so these three things here will be the conversions. When we go back and plug this into our, we use the normal equations. So this was a way for us to kind of rewrite through a transformation this hypothesis function here in terms that allowed us to have linear combinations. And by doing this, we're able to solve the normal equations. So this, it provides us a way way to solve the x transpose x. And now we have this beta coefficient parameter vector, which equal x transpose z vector. So we have this beta coefficient, which is this is our new parameter vector. Remember, that's where that W vector would have been. And then the Z1 is would be our new observation vector. That would be, again, previously the y, which is what we've substituted here. So this would be our new observation vector. And when we look at our new observation vector, which is this what it looks like, remember we have y, which was equal to our h of x. So that's what we did the substitution there. And then since we had to use the log, we had to use the log on this side to break apart this w dot and the e, which means we had to put a log onto this side. So when we take our new observation vector, which would be our y's, part of this conversion, the roadmap that we need right here, is to apply log to all of them. So this is why we need, like, this conversion for these three things is crucial, because those have to be applied into the normal equations that we're solving. So into our observation vector and into our new parameter vector. And that's part of this new hypothesis function that we're creating that holds these beta coefficients. Because this form right here is exactly what we were looking for. And we fit this into this new form by adding the logs and doing all this stuff. But then crucially, we need to provide this conversion because we don't want to have our final form be this. This is still pretty messy. We want it to follow this. So that's why we've done that. And now this is completely linear in its parameters. And we can have a solution to the normal equations now, which will give us our new parameter vector, which is going to be b star, and then our new observation vector from that, because it's no longer we're not trying to find the best, we're not trying to take our beta coefficients and multiply and dot product through our design matrix to find the best y. We're doing that to find the best log of y now, because again, we have this conversion that we need to keep in mind. So that's what's happening here. And we've had two approaches to this now, where we've had things that are given to us in this form already that are very nice, and we can just go ahead and straight solve for the normal equations and then determine whether the matrix is what that is, and if it's good to go, then we can just get our solution. But if it's not invertible, then these are the things that we have to do. We also have had now where we have our hypothesis function with something that's not linear, and we're able to transform it, and that's good. But there's also a third case now, and this third case is what's going to lead us into gradient descent, because in some cases, for example this, we cannot use any amount of transformation to simplify this or change it such that the w sub 1 here is removed out of the sign. So in this case, we cannot solve for this mean squared error through the normal equations. We have to use something else, and that thing we have to use is gradient descent, which is a generalized way of minimizing functions. So we will look at that coming up after we do a quick practice problem, or after I allow all of you to do a quick practice problem. But that's where we're going, because we have three cases. They're already linear combinations. Boom, we're good to go. They're not linear combinations, but we can do a transformation to put them into a linear combination pattern. Boom, we're good to go. Or nonlinear hypothesis functions that just cannot be transformed, in which case it's a no-go. We have to use something like gradient descent, which we'll talk about next. But why don't you go ahead and try to answer this question. Which hypothesis function is not linear in the parameters? And I'll give you just pause the video, and then we'll, in a few seconds, we'll go ahead and talk through it. Okay, so let's step through each of these really quickly. Remember, our goal is to determine for these hypotheses functions which is not linear in the parameters. So we want to identify ones that follow our case where we're summing some w multiplied by some thing and summing up those. And we want to ensure that there are no w's occurring in the something, that they're all here. And based on the information that we have, let's go ahead and begin to look at them. So A, we can begin by looking at our w's. We know we have one right here, and we have another one right here. So we might think, okay, well, W1, W sub 1 times this stuff right here, that's good to go. And W sub 2 divided by X times, okay, that looks a little interesting. Perhaps that is not linear, but this would be, because we would just take, we could just rewrite this as being W sub 2 times sine x2 over x1. Thus, we would have our W by itself, so that's good. This we were unsure about, but now we're good. So this is good to go. Okay. Let's look at B now. So for B, we have this W in the exponentiation. So this is already failing. This which hypothesis function is not linear in the parameters. So we'll go check the rest of them and come back to B. C, C looks perfectly fine. This is in the form of W sub 0 plus W sub 1 times X. And remember, these are the these are in the form of W sub 1 times X1 plus W2 X2. So these are, this is good to go. This is fine. Let's look at D. And that's also, because I forgot to do it, let me just put a little thing above here and say that's good. Okay, for this one we have this one right here, 2 right here, and this is perfectly fine as well. So this follows linear combinations of the parameters. That's good. We already know that 3 of them are good, so we know that this can't be the answer. So I guess technically that's fine. So that leaves really this one. Now, of course, we could probably clean this up with the transformation, but for all intents and purposes, this would be the answer because it's not already linear in the parameters. But of course, we could transform it. But if we're looking at this question, and we didn't say to assume no transformations, then you'd go through these and see that B, even though it could be transformed, is still the best answer because it is the only answer out of all these. If E instead was none of the above, then you'd want to ask if there's an assumption of transformations. Okay, but since E is not none of the above, say B is the best answer. All right, so before we jump into gradient descent, I want to just real quick go through the modeling recipe again because we haven't looked at it in a little bit, and I want to kind of just provide a slight scaffolding for all of you to see how far we've come, what we've done. Remember, the point of the modeling recipe is to really talk about what is the best way to make predictions. So this is really so given some data and targets like our y's, how do we make good predictions? So that's the goal here. And we've seen that, the most important thing to start with is to choose a model. And we've looked at several models. We've looked at the constant model, for example. So that would be just, let me write that a little bit better. We looked at the constant model, which would just be our hypothesis function, and that's going to equal just some constant. We've also seen things like simple linear regression, where we have our hypothesis function, and that's going to equal W naught plus W sub 1 X, and this is the simple linear regression one. And we've also seen a slightly more complicated multiple linear regression model. And that was in the form of our hypothesis function, but now x is a vector. And we have still our w naught plus our w sub 1 x with feature, the first feature, plus our second parameter with our second feature, plus our n with our nth feature. And well, I suppose really before we were using d, so I'll keep that the same, and I can write this. Actually, I can write this all a little bit better. So for D features. And we had two ways of thinking about that. One is if we wanted to get, well, I'll write this first real quick. This is, and you had for a, I'll put that in purple, for a single prediction, and then for all predictions, and that wound up being in the form of, for a single one, we had the idea of the augmented matrix. So that would be our W, our augmented X vector for the feature. And then for all the predictions, we had our hypothesis vector, which equaled our design matrix times some parameter vector. And that was for all the predictions for all the data points. Okay. Next, once we decided which model we wanted to use, we had to pick a loss function. And we looked at several loss functions. So for example, we looked at squared loss. Which would be, turn that off last time, was our y sub I minus whatever our hypothesis was, x sub I, and that is going to be squared. And this is our actual, and this is our prediction, and whatever the difference of that is squared gives us our squared loss. We also had this idea of an absolute loss, which was y sub I minus h x sub I, just with an absolute values. We also had our 0,1 loss, and yeah, there's several other we've looked over throughout the different homework problems. But you choose a loss function, and then after that, you try to minimize the loss function, which is the same thing as we've been calling empirical risk, to find the best model parameters, which would be your W sub, W naught star, W1 star, and however many W's you have in your parameter vector, or of course, it could be H star. And for that, this is either mean squared. So we could, if we were looking at, for example, a constant model with, let's say, squared loss. So we could say then that would just simply be for h, this is our 1 over n, for y sub I minus h squared, which essentially just winds up being the mean. I guess that would be nicer, of your y1, oops, all the way to your yn. We also, if you had, for example, your multiple linear regression combined with squared loss, then that would just be squared. And here we have our, we're trying to find what the optimal parameter vectors would be. So that's just 1 over n. And then we have the length of the error vector. So your predictions minus the design matrix dot product with the parameter vectors w naught, w sub 1, so on and so forth. And that's all squared. So in context, this is what we've been doing, and everything that we've done so far is either to show how these models work, to show how these loss functions behave, and to show how you actually go about determining the optimal H star or the W stars. And it's either been looking at those or trying to build up the theory and intuition behind how all these things work. So for example, the projections onto spans when we did linear regression, so on and so forth. So this is, everything we've done so far has been building up to this, because this general modeling recipe is by and large how all machine learning algorithms work. That is not to say perhaps unsupervised machine learning algorithms, that the clustering and stuff like that is a little bit of a different animal, as well as also reinforcement learning, things like that. But by and large, all supervised machine learning models work in a similar way. They just wind up doing things either more either differently or more in more complex manners, but they all follow the same general patterns and ideas. They just get more difficult, perhaps, or just think about things a little bit differently. But they all follow the same modeling recipe or the same basic principles. That is to say, though, that the model would certainly change, the loss functions can certainly change, and what really does change, though, is the minimization of that loss, trying to find the optimal model parameters. That can widely differ based on the machine learning model that you're using. Whether you're doing like support vector machines, or you're doing things like with mixture models, or you're doing stuff that involve like neural networks, these things can definitely get much more complex. But by and large, this is a good, you could say, theoretical foundation for those other complicated things. Okay, so we're kind of departing now the kind of hand way of doing things, and we're going to an area with gradient descent where we really can't solve things by hand so much anymore, and we need the computer to do stuff for us. Or leveraging the computer's power can be very useful for solving extremely complex functions, which is what gradient descent tries to do. We've done things so far where largely we've tried to minimize empirical risk functions, for example, by setting the derivatives equal to 0 and solving for the derivatives. And that was the kind of, using calculus to solve for these or instead of using calculus, you might have decided that, for example, in the case of, well, if we're trying to do something, for example, with this type of absolute loss, then like simple linear regression with absolute loss, then we had to use multiple loops and kind of like brute force approach to solving these. And then we've also had stuff where we had multiple linear regression, and we had to use spans and projections and linear algebra. And we like linear algebra, so that's okay. But it's also very tedious, so it's a little bit of a upsetness going on there. So what do we typically want to do? Well, as data scientists, we want to leverage computers to help do things. So we want to have some sort of general approach to solving or to minimizing functions. And if we have a differentiable function, which by differentiable we means that, I'll put this over here. Actually, so by differential we mean that a derivative. Oops. So derivative exists, and it exists in all places on the surface of the function. And if we can assume that it's differentiable, then what we can do is we can set the derivative equal to 0 and solve for it. And that works pretty well. But when we get into extremely complex spaces where things may not be necessarily, like a simple concave shape or convex shape where there's like a bowl, but we're in a very kind of difficult landscape. So, for example, when we're in something like this, even in a 3D sense, this is easy to minimize. But when we're in more complex functions like this type of stuff can be very difficult to minimize, or for along like saddle points, these things can be difficult to minimize. And so what we really need to do is have a sort of general approach. So for example, let's say that we have this function here, and that's this. This is some 4th degree polynomial function, and it looks pretty scary. And how would we go about doing this? As well, we would take the derivative and set it equals 0. We can solve for it. We can take the first derivative, and if we I'll do this in green, blue, and if we did this, this would be df dt with respect to t, and this would be 5 times 4 is 20t to the third minus 3t squared minus 2 times 5, 10t plus 2, negative 9 goes away. So that's great. We've got this. We can now kind of work with it. However, a 3rd degree polynomial thing like this is there might be a mechanism that we can use to solve this by hand, but it's very nasty. And of course, it's nothing stopping us from having 10th, 20th degree polynomials, and we take the derivative and go down to the 19th. Like how do we solve these things? It's not really feasible to do this by hand, or it's impossible to do it. And so we need a different approach when we can't really comprehend the entire landscape of the function, its entire surface area. So let's say that we have something like this, and we want to. This is what we had before. And we want to minimize this where the optimal parameters that we can learn are here. In the real world, when you're dealing with machine learning in extremely complex environments, you'll never really get to a global minimum in extremely complex functions. But you want to try and find really good local minima to fall into, and find good general solutions to or good to come up with good quality parameter vectors. But how do we kind of solve this? What can we really use in our toolkit to look at this? And if we think back to calculus, we know that we can take derivatives as we go through the surface of a function or along its surface, and or in this case, travel along this line. And we know that a function or a derivative taken at any point on this line, when we have a tangent line, so for example, if we have a point right here and we take a tangent line to this point, whatever the slope is of that tangent line tells us about the derivative. And more importantly, it can kind of tell us, one, how close we are to a subminimum, as we get closer, the derivative becomes smaller, and as we go, also we could know if the derivative is positive or negative, which direction we want to go, because if it's negative or if it's positive, we know that we want to go either left or right or some direction. So taking the derivative tells us a lot about the local area that we're in, on these the surface of these functions, and we can use that information in some sort of computational process, which is going to be gradient descent, to allow us to try and calculate the best way to go about moving along the surface of this function to find an area that's a local or global minima. It's kind of like, you can think about it, if you're hiking and we're at the top of the mountain currently, and our goal is to get to the bottom. Well, if we could see the entire mountain, then we know where to go, right? That's easy. And for extremely simple functions, we can see the entire function and the entire space and know how to get to the minimum. But if it's extremely cloudy out to where you can't see more than a few feet in front of you in any direction, then how do you get to the bottom of the mountain? Well, you can tell, from the few feet in front of you if you're going immediately downhill or uphill, or if you're going parallel to the ground. So you look around you and you see, where is the steepest direction, and then I'm going to go that way. And that's kind of like taking the derivative. In these extremely complex functions, you can't see the entire, you can't see in this case, the entire mountain. So by taking the derivative, we can see and learn about the space around us, and then use that as a way to move along the surface to try and find these local or global minimas. And that's really a nice way to approach these problems. So, suppose we're given an initial guess to the value of t that minimizes the function f of t. So we want to go to the minimum, and we know that we want to end up here. We don't want to go here. So how do we move along this function? And at any given time, at any given location, so anywhere we are, we can always know what the slope of the tangent line is and where we are in the function. So one of the things we need to determine is, do we have a positive or a negative derivative? In this case, if we have, maybe I'll put this in yellow, if the derivative is positive, so if the derivative is positive, then we want to go and move to the left. So, because the minimum must be to the left. So, which means we want to go this way. And if we keep doing that, let's say we move to the left a little bit and then take the derivative again, we see it's positive, but it's also getting smaller. Then we move to the left, then we move to the left, then we move to the left again. And then we take the derivative again, then we move again, then we move again. And hopefully, once the derivative gets very small, we know we're about at the minimum, and we can stop. And we know that by doing that operation, the parameters that we found are likely to be very good parameters. And in extremely complex cases, we may never know if they are W star, like the best possible ones that you could get, but we know that they could be very good quality ones. For example, like if we're in a function which is like this, we might say that, okay, all of these ones are bad, but if we can get to some local minima like here, or the global minima here, or another local minima here, then you know what? This could be good enough, and the best. This, we don't want this, we don't want this, we don't want this, or this, or this, or this. So as long as we can get to some good space, then we'll be good. Now, how do you determine that? Well, that's in more complex machine learning models. You do like validations, and you check to see how well your model is performing in these validation phases. And when you think that you're doing quite well, then you can go ahead and take those weights as being perhaps weights that are good enough for your use case. But this is the kind of thing that we want to do. And the same works if we're going the opposite direction. If the slope of the tangent line is negative, then that means that we need to move to the right. So in this case, I'll do this in here. I say if negative move right. Well, sorry, this should be derivative move right. So these are the things we want to think about when we're looking at these spaces and why we care about taking the derivative along this surface. Now this is the precursor for how the gradient descent algorithm works. Okay, so here's the intuition behind gradient descent, and it's that you want to pick some sort of initial state. We'll call that T naught, and that's where we think the subminimum might be. But it's just it's a good educated initial guess. And then we take the derivative, and when we take the derivative, we have an update rule. This update rule is right here, and this update rule tells us what do we do. And that depends on what the derivative currently is. So if the derivative is greater than 0, that means that it's positive, and we want to go in the opposite direction, so we don't keep going uphill, we want to go downhill. And similarly, in the same vein, if it's below 0, negative, then we want to increase and go uphill. So the way we do that is with this update rule. And maybe make that explicit right there. So this is the that's the gradient descent update rule. And the reason why there's this minus sign here is because that would tell us to go into the opposite direction. Specifically opposite direction of the derivative, and that's this part right here. So we have this initial state t sub 0, and then we're going to have t sub 1 or t naught, and then t sub 1, which is going to be an update where we plug in our t naught and we apply it to the derivative. And there's going to be any number of t's, t sub 1,000, t sub 100, however many iterations gradient descent runs for, is going to dictate how many t's we have. And we just keep replacing, the next iteration, it becomes t2 equals t sub, or t1 minus the derivative of with respect to t1. And that's why it's the update rule. It's constantly updating based on where you are in the function. So to make, that's pretty good. So if the derivative with respect to t naught is greater than 0, then t1 equals t naught minus some sort of result, and then the opposite is true, of course, if it's less than 0. So that's the general intuition, and really our t's, t naught, t sub 1, t sub 1,000, whatever, they're just guesses for what the best t, that is the t star, is that minimizes the function. So I guess I will write that. So there exists some t star, right? And that t star minimizes our function. And t naught, t sub 1, t sub 2, all the way until t sub n are guesses for t star. And we improve, or we try to improve Tn via this update rule. So that's the intuition behind gradient descent. Now, the whole point of gradient descent is, again, to minimize the differentiable function. And there's a couple things that need to be decided when we use gradient descent. And the most important one, well, I will say this, there are a lot of things. Gradient descent does get much more complicated with different things like adaptive learning rates and momentum. But by and large, for simple gradient descent, the thing that we really care about is this what's called a learning rate or a step size. And that's alpha right here. And this is sort of, that's called a step size, but it's really a multiplier that's used. And the multiplier is really what's determining how large of a step we take in between our T1, T2, T, all the way to N, how big those steps are. And that's really important because if you have, some function like this, with the learning rate, if you start here and your learning rate is really large, your jump might be there, and then there, and then there, and then here, and here, and here, and here, and here, and you might even go out. That's if your learning rate is too large. If your learning rate is too small, then your T naught might start here, then T1, T2, T3, T4, T5, T6, T7, 8, 9, 10, and then it just stops. And it never gets here. But if your learning rate is just right, Goldilocks principle, then T naught is here, and then T1, T2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and you stop there. I mean, that's like T80 or something. So the learning rate is really important. And there's different strategies for picking optimal learning rates. Really, for some reason, in industry or for a long period of time, a learning rate of 0.09 was very good. It's just, people have a lot of trials, and this wound up being a very nice learning rate. And there's some papers that suggested it, but regardless, picking a learning rate is important. But you need that, and it needs to be a positive number. And then you need to pick an initial guess, and then you just repeatedly update this rule. So the update rule is really the key here. And we're going to go for I iterations until we have convergence. And convergence is when the delta between t's doesn't change very much. And when you have that, that's how you know to stop gradient descent. And there's lots of mechanisms that you can employ in code to determine when to stop, when the delta between t's doesn't change very much over a set number, right? You can imagine something like this, where you are learning and then and then you stop maybe after like 20. But if you had just gone to maybe, let's say, 100 iterations, then you'd go back down again, and then your T starts to change quite a bit again. So there's lots of, there's certainly an art to this. But yeah, your alpha is here are the step sizes. Small steps or big steps, they're all important. And when the derivative is small, that means you're closer to some minimum, and you'd want to take smaller steps. Those are kind of good overall ideas to think about with gradient descent. And one of the last things that we'll talk about with gradient descent is this idea that it's a numerical method. And numerical methods are just approximations for some solution that we can use for a computer, because we can't often get to the global minima. We want to hit a good enough minima, and some combination of step size or learning rate, a good initialization with T naught, and then good strategies for when to stop allow you to find good local minimas that can approximate the answer to the solution or approximate that T star. So that's the idea behind why gradient descent works so well and how it offers a general solution for these kind of minimization problems. Again, we're not finding often the optimal or the best or theoretical best solution, but we're finding approximations. And that's really the important thing to consider here. So next up in class, or in the next lecture, we'll kind of dive a little more into gradient descent. And we'll talk about this idea of global versus local minima convergence. We'll think a little bit about how to choose a good step size, and how is gradient descent used with multiple variables. So those are with those keys, then you'll really understand gradient descent. And when you go to learn things like neural networks and deep learning, you'll understand the minimization process and be well equipped to dive into things like the backpropagation algorithms and stuff. So that's all for this lecture.